Hello everyone. Are you able to hear me?
Yes, ma'am.
So let's wait for 2-3 more minutes, and after everyone comes, we'll start the session. Visualize and process the remote sensing information or remote sensing data. So this is an example of Landsat data. This is a surface reflectance data, so that's why it's not surface reflectance we get after processing the DN values, so that's why it's not within 0 to 255 strictly. But I just wanted to show you the distribution of the histogram. So if so, this is an image over Kanpur on 14th July 2023. The white pixels that you can see on top, that's the cloud cover, which have higher reflectance values. And on the right side, there is a raster histogram. So if you look closely, this histogram is skewed on the left side, like this previous image. And the maximum frequency is around 7 to 8,000. So, and that is why most of the pixels in this image appear darker. So this is it's the real life example, so that you people can will be able to visualize better, and you'll be able to understand how the remote sensing data is actually looks, and how we can play with the data. Hello. Are you able to see the next slide?
Yes, ma'am.
Does anyone have a question?
In previous slide, the relating that digital numbers, will you please show that page in which you have written everything?
This one?
No, no, you have written something in red.
Yeah. So I have changed it here, but it's there is a slight lag.
Okay.
So it will come. Yeah. This one?
Yes.
Huh.
But, you correlated something in this whatever you have written with respect to previous image, whatever you have shown, I think. Would you please repeat that thing again?
Yeah. So I told, right, that the lower DN values, they will correspond to darker areas which are not reflected
First one is
Yes.
geostationary.
So why is it called geostationary?
Because it
Because
remains on the same point across
Uh,
on the
and
sky.
rotates from west to east.
right, right. So the time period of revolution of this satellite will be same as that of, I mean, it
That
will
of
be equal to 24 hours. It will be same as Earth's rotation. So that's why it keeps looking at the same spot all the time. Okay, what is the second one?
ma'am, is this geosynchronous?
No, in
Low Earth orbit.
geo, yeah, this is a low Earth orbit. So in first case, the satellite it has to stay all the time over the equator. In low Earth orbit, it revolves at a small angle to that of the equator. So because it makes a small angle, it's called low Earth orbit. And in the last one,
Polar
Polar
orbit.
orbit.
Orbiting
yeah,
satellite.
yeah. So you have to find the 100% first in order
Is,
to
is
get the
there any
50%.
calculation, ma'am?
Yeah, so this is your spectral wavelength. Lambdas. Okay, I don't know if this is the right terminology. So this is your central wavelength, which will be at the center of your delta lambda.
Okay.
So yeah, so you can solve the question now with this background.
C option 665 to 675.
Yes, that is right. So our lambda central here, it's given as 670, and the full width half maxima, no, the bandwidth is 10 nanometer. So this area, this much is 10 nanometer. So the range will be it will be 5 nanometer on this side. Um, yeah, 5 on this side and 5 on this side. So it will range from 665 to 675.
5 and 670 minus 5.
Yeah, 670 minus 5 and 670 plus 5. Is that okay?
Got it, ma'am. Got it.
Okay. Yeah, someone has raised hand.
Hello,
Huh.
is my voice audible, ma'am?
Yeah, you are audible.
Yeah, ma'am, you have discussed about FWHM, right? So in
Hmm.
this, you have some values with respect to the wavelength. So we have calculated. So if the values are not given, so how can we find out the highest FWHM for the given peak?
For the given peak. Yeah, so it
Yeah,
will be, so you have
that is
your
with respect to the histogram. That is the data which you have given. Instead of not giving the data, how can we calculate considering the maximum and minimum value?
maximum and minimum values of what?
Uh, I mean the one which you have discussed in that you have given the frequency data as well as the wavelength data. So based
Hmm.
upon that we have calculated the wavelength range, right? So
Right,
if
right.
that values are not represented and only the graph representation is given, so how could we calculate the FWHM for that case?
Okay. So, uh, so as far as I know, uh, yeah, you can detect the point with highest intensity, right?
Yes.
So this is your 100%. And then you find 50% and draw a line parallel to x-axis. Now, the 2 points at which this line intersects the curve, that is your range.
Okay. Thank you.
Yeah. So here you will get one lambda, here you will get another lambda. Is that okay?
Ah, okay, ma'am.
Yeah.
Thank you.
All right. So this is the next question. Okay, the slide has not changed. Wait. Okay. A hyperspectral sensor with 200 spectral band covers range from 400 to 1000 nanometer. So what is the average spectral resolution of this sensor in nanometers? Does anyone want to try?
Is it 8?
Someone says 3B.
Ma'am,
Okay.
can you show us the calculation for this question 3?
Yeah. So this is the range 400 to 1000 nanometer. Okay. and there are 200 spectral bands. So there are bands with very small spectral range. So there will be 200 such bands. All right. So the total wavelength range over here is 1000 minus 400. It's 600 nanometers. And assuming there is no overlap between the bands, so we have 600 nanometer wavelength range and 200 bands. So each band will be 600 divided by 200. So it will be 3 nanometers.
Got it, ma'am. Good.
So next question. Spectral resolution is essential in remote sensing because
Option C, ma'am.
yes, yes. So because spectral resolution, it provides information about the composition and properties of the Earth's surface and atmosphere. So that is that fine with everyone? Hello. Okay, we'll move forward. Yes, which type of remote sensing sensor is likely to have higher spectral resolution?
Hyperspectral sensor, ma'am.
Yeah, right. So we just saw that in hyperspectral there are very small number of bands. So here the spectral resolution will be the highest. Right. All right. So we'll solve a numerical on spatial resolution. So yeah, I'll give you guys some time so you can solve and let me know your answer or type it in the chat box. Anyone else? Yeah, so most of the people are getting 5 meters cross 5 meter. Is anyone else getting a different answer? Okay, fine. So we'll look at how it's solved. Uh, yeah. So we have an area of 20 kilometer by 15 kilometers. All right. And there are 4,000 pixels in this row and 3000 pixels over here. Right. So our total area (20 cross 15), and we'll convert it to meters. Meter square, and we have total number of pixels. Sorry. So area of 1 pixel will be equal to mm,
So it will be 300 by 12.
yeah. So 300. So this is 25. Area of 1 pixel is 25. So its dimensions will be 5 meter cross 5 meter. So I hope everyone got this.
Got
We'll
it,
go
ma'am.
to the next question now. Okay, so you can try this question for a while. It's, I mean, almost similar only, so it should be easy. So we have to count number of pixels. Okay, and be careful about the units. Does anyone want to change their answer?
So in case, ma'am, we have to convert it in either of the units, like either all in centimeter or all in kilometers.
Yeah, or you can convert everything in meters and keep it in SI units. Yeah, someone is getting the right answer. Milind. Anyone else getting the same answer?
Yes, ma'am, got the same answer.
Okay. Okay, let's see. So, yeah. This is 1 kilometer by 1 kilometer, and we have certain number. Okay. So minimum value that can be represented by a single pixel in the image. You can try solving this for a while.
4095.
Yeah. So it's 4095 or 4096.
4096 it's coming.
Okay, let others also reply in the chat and then we'll discuss. Anyone else? Okay, so the radiometric resolution is 12 bits. So total number of pixels in this image will be 4096. But remember what when we saw the for the 8-bit image, it was to the power 8, and total 256 values of pixels were possible. But since we start from 0, the values range from 2 to
0 to
255.
255.
Yeah. So similarly, in this case,
It will be 0 to 4095.
4095.
So my answer will be 4096 or 4095.
No, it will be 4095. So first question was different. It was asking that how many total distinct levels, I mean distinct values are possible. In that case, say 2 to the power n. But then when we are talking about what value of the pixel it will be, in that case, it will be 2 to the power n minus 1, the maximum value.
Okay.
Yeah, so in this case, it will be 4095, not 4096. Is everyone fine? Okay. Yeah, so a thermal infrared camera has a radiometric resolution of 8 bits, and it's used to capture data over a temperature range of -20 to 100 degrees Celsius. So calculate the temperature difference represented by each brightness level. So you can try this for some time.
Ma'am, shall we first convert this centigrade into Kelvin?
See, because it's the temperature difference, you need not convert it.
Okay.
Povehi 0.468 degree per pixel. Anyone else?
Yes, ma'am, 0.46875 degree per pixel.
Others? Okay, we'll solve it. Yeah, so the radiometric resolution of the camera, it's 2 to the 2, I mean it's 8 bits. So total number of radiometric levels will be 256, and the values will range from 0 to 255. Okay, so yeah, the temperature ranges -20 to 100. So the total range will be like 100 minus 20. Yeah. And it will be 120 divided by 256. So that is equal to 0.46875. So if you want to visualize this, so our temperature ranges, it starts from -20. So your temperature at -20 degrees Celsius, it will have the value corresponding to 0. Then this is our increment, right? So for 1, our value will be minus 20 plus 0.46875. So, okay, whatever this is. So this will be your 1. Then, so it will be minus 19 point something. So then for your 2, it will be minus 20 plus 2 into 0.46875 and so on. And your 255, it will correspond to 100 degrees Celsius. So if this is the image, so let's say this area in the image, it represents some region with very hot temperature and rest of the region has colder temperature. So this area here, it will appear brighter because it will have higher DN values. So here our values will be like here 255, 254, 240 and so on. And in the colder region, the values will vary like 80, 90, 70, 40, 30 and so on. So depending on how the temperature contrast is, right? So there are different ways in which this data lake format can be arranged. So, and so these are the different types in which this data format is there, in how we will arrange different bands, right? So in band sequential, we have band 1 completely, then we have band 2, y2, y3, y4, y5. All right, and then third band we have. Okay, in band interleaved by line, so what happens is one line from first band, then one line from second band, one line from third band. So this instead of taking the whole image, it takes the information line by line. So like we have suppose first line x2, x3, x4. Then we will have second line. No, then we will have first line from second band, y2, y3, y4. Then first line from third band, and so on. So in this case, you have, I mean, all the lines are taken first. And in case of band interleaved by pixel, it is like first pixel of first band, then we will have first pixel of second band, then there will be first pixel of third band, then again there will be first pixel, second pixel of first band, second pixel of second band, second pixel of third band, then we will have x3, y3, z3, and x4, y4,
But is
z.
this VIP you're teaching?
Yeah,
Is this VIP you're teaching?
yeah. This is a band interleaved by pixel. Then we will go to the second line, and again second line first pixel of first band, then second line first pixel of second band, y5, z5, and so on. So these are the different data format. So there might be questions in assignments and all where you are given three different bands, and you are asked to um, arrange them in different type of file formats. So this will come when you're, I mean, this will be more useful to you when you are dealing with actual images. I mean, only simply studying the theory might not be this interesting for this. So yeah, then we have electromagnetic radiation. So yeah, this is a very easy question. So do you guys want to try this first? This was covered in the second lecture, so I hope you will be able to solve this.
Ma'am, 6 into 10 to the power 14.
6 into 10 to the power 14 hertz. Anyone else? Okay. Right. So as we know that frequency so the constant here is speed of light 3. All right. So yeah. So here this is the relation between frequency and wavelength, where c is the speed of light, which is equal to 3 into 10 to the power 8 meters per second. So here we have given the wavelength. So lambda equals to 500 nanometer. Now first we'll have to convert this nanometer to meters. So nano means 10 to the power minus 9. So we have 500 into 10 to the power minus 9.
Ma'am, are you writing? It's not visible, ma'am.
Oh, it's
Yes,
okay.
ma'am.
Wait, let me refresh my screen. Yeah, I was writing. Uh, it's visible now, right?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay. Yeah. So this is 6 into 10 to the power 14 over a second. Oh, it's 10 to the power 14 hertz. Okay. Now try this question. A radio wave has a frequency of 100 megahertz. Calculate its wavelength.
Ma'am, is it 33.3 into 10 to the power minus 8?
33. Anyone else?
Or we have to change the unit for megahertz?
Yeah, so 100 megahertz is 100 into 10 to the power 6 hertz. Anyone else getting a different?
Now I'm getting 33.3 into 10 to the power minus 2.
0.03 into 10 to the power minus 4 meter. Mm, 3 meters, right? Yeah, so we'll see. So here we had nu is equal to c by lambda, right? So now we have the frequency over here. So lambda is equal to c by nu. So our c is 3 into 10 to the power 8 meters per second, and nu is 100 into cancelled. So we have 3 meters. Is that okay? This 10 to the power 8, 10 to the power 8 gets
Yes, ma'am. Yes.
okay. So this is so you guys know relation between energy and wavelength, right? So E is equal to hc by lambda, or E is equal to h nu. So this relation is being used for this question. Won't change megahertz into hertz. Where? We did change megahertz into hertz, right? Here 100 megahertz is 100 into 10 to the power 6 hertz. Did I answer that?
Ma'am, can you show the next slide? Yes, ma'am. Ma'am, its answer I have got 4 into 10 to the power minus 19 joules.
Yeah, it's close. Yeah, 3.97 into 10 to the power minus 19. Yeah. So it's right. So E is equal to hc by lambda. You have 6.626 into 10 to the power minus 34. C is speed of light, 3 into 10 to the power 8. So just take care of the units over here. So this is joules per second into meters per second. No, sorry, this is joule second.
Joule into
And here you
second.
have, yeah. 500, and nanometers will convert to meters. So 500 into 10 to the power minus 9. So yeah, so I did this calculation and it's around 3.9756 into 10 to the power minus 19 joules. So second gets cancelled, and here this was in meters. So meter is cancelled. So the unit is joule over here. And so every time whenever you are reporting any values, you should write it with the unit. So that's a good practice. So everyone got this answer, right?
Yes, ma'am.
Okay. Next question. An X-ray photon has an energy of 100 kilo electron volts. Calculate the corresponding wavelength of the X-ray. Into 10 to the power 7. Okay. Others can try. Anyone else?
Ma'am, what will be the formula used here?
Yeah, this is the same formula, but first, can you mute? I think my voice is my voice echoing.
No, ma'am.
Okay, okay, fine, fine. Yeah, sorry. So first, we saw that our energy was in joule. So joule is the standard unit, right? So here our energy is given in kilo electron volts. Kilo electron volts, right? So let's first.
First we have to convert it to electron volt. Then 1 electron volt is this much of joule it is given.
Yes, yes, that is absolutely correct. So first 100 into kilo is 10 to the power 3. So we have these many electron volts. Right. Now we will convert electron volts to joules. So this conversion here is given. So we have 10 to the power 5 electron volts and 10 to the power 5 into 1.602 into 10 to the power minus 90. So it will be this many joules. Right. And now we use the same formula. E is equal to hc by lambda, corresponding wavelength. So wavelength is unknown, everything else is known. So lambda will be equal to hc by E. So this is 6.626 into 10 to the power minus 34, 3 into 10 to the power 8.
By 1.60 into 10 to the power 19.
So this will be 1.602 into, so this minus 19 and plus 5. So this will make 10 to the power minus 14. Right. So my answer is coming around 12.40 into 10 to the power minus 12. Is any one of you getting this? I mean, close. Are you guys getting this?
Yes, ma'am. 12.4 into 10 to the power minus
Meter.
12.
Yeah, yeah. I did unit. So this is per second. This is H, this is C divided by joules. So joules, joules, second, second. So the unit is meters. 12.40 into 10 to the power minus 12 or 1.24 into 10 to the power minus 11 meters. You're getting this. So the unit curve. Okay. So the next question is on Stefan Boltzmann law. So Stefan Boltzmann law, it relates the total emitted radiation from a black body with that of the absolute temperature. So E is equal to sigma T to the power 4. So it says that total emitted radiation from a black body is directly proportional to the force power of the temperature. And sigma over here is the Boltzmann constant. So value of sigma is 5.67 into 10 to the power minus 8 watt per meter square per Kelvin to the power minus 4. So try to solve this and then we'll discuss. So you are given T and you have to calculate E. So first you have to convert this temperature from degree Celsius to Kelvin. So the conversion from degree Celsius to Kelvin is so you have to add 273.15 to convert it to Kelvin. So your temperature will be 226.85 plus 273.15. So this is 500 Kelvin. Now it should be easier.
So, ma'am, I will now do 500 to the power 4
Yeah,
into,
500.
into constant.
Right. So you have to make sure that the temperature is in Kelvin over here, because here in the constant it's Kelvin.
Ma'am, it's a very long answer that I'm getting.
Mm,
It is 3,543.
Yeah,
yes.
yeah.
Yeah. Uh, I'm getting 3,543.75.
3543.75, like that.
Yes,
I got.
yes, yes.
Yeah, yeah, yeah. That's right. That's right. So, yeah, after this, it's just E is equal to sigma t to the power 4. So we have 5.67 into 10 to the power minus 8. And t to the power 4 is just 500 to the power 4. So, yeah, it's 3543.75. And the units, watt per meter square per k to the power 4 into k to the power 4. So this will be in watts per meter square. Is that fine?
Yes, ma'am, yes, ma'am.
Okay. So we'll do the last problem and then we'll wrap up for today. So try to solve this. So a black body is a body which emits at the highest. It emits at the highest possible rate. But other objects which are, but black body is an ideal case, right? So other objects which are not a black body, they will emit at a lower rate, and then emissivity is the ratio at which it emits with respect to the black body. So emissivity is uh, emissive power of a body to that of the emissive power of a black body, right? So yeah, so you can use this to arrive at your answer. Are you able to get it?
It is directly 2000 by 4000.
Yeah. That temperature information is unnecessary over here.
Yes, yes, yes.
Yeah, I think you people got confused because of that. Yeah, so it's just 2000 over 4000. So it will emit at half the rate as that of the black body.
Ma'am, answer is 0.5.
Yeah. So temperature is because it's, the value doesn't matter, but the temperature of the given body and the black body should be the same in order to compare. Yeah, so it's 0.5. Is it clear with everyone?
Yes, ma'am.
Okay. So thank you so much for staying so long in this session and for actively participating. It was my first tutorial session and it was a really good experience. So thank you all, and we'll meet again next week. And let me know if you have any questions or something in the, you can ask in the forum, or yeah, I'll share the drive link in the chat box. So you can go to this so I'll upload the lecture over there. Mm.
Ma'am, can we get the video recording of this lecture?
Yeah, you'll be able to get
And
that.
the presentation, ma'am.
Yeah. And this is my email ID if any of you want to ask anything.
Thank you so much, ma'am. It was a nice session.
Thank you all. Thank you.
Ma'am, I have a question.
Hmm.
Ma'am, in what and all days do we have this online meet section?
Yeah, so there are two live interaction sessions for this course. One is on Monday 6 to 8 and the other one is Tuesday 6 to 8.
So every week we will have 2 day online meet, right?
Yeah.
Okay. Thank you.
Okay.
One more thing, some video lectures have been shared actually every week. If any PDF can be provided for the lecture.
PDF as in, I think there are reference books and all mentioned in the lecture itself.
Yes, it is mentioned, but the whatever lectures are there means whatever the teachers are teaching. So if a brief PDF can be provided, because last time I also did one course, they were providing PDF for every week. So
Yes, ma'am.
while solving the problems during assignments, also it is very helpful actually.
Okay. So actually, I mean, I can't do anything about it, but I'll
You can
find out if
communicate.
it's. Yeah. I'll ask and I'll find out.
Okay. Thank you very much.
Okay. Thank you all. Any does anyone else have any question?
Ma'am, can we get yesterday's PDF?
Yeah, so I think you will be given the links to all the material. So there will be a drive folder in which material from every week will be uploaded, and you will be provided a channel link where you can go and watch all the live sessions, the recordings of all the sessions.
Thank you, ma'am.
Okay, thank you.
Yeah, hello, ma'am.
Of course are available in it.
Ma'am, there is no file in the drive, ma'am, actually.
Hello.
There is no file in the drive. If I
Yeah. So this was the first lecture, no? So after the lecture, it will be uploaded.
okay, fine. Thank you.
Okay. Yeah, you have to submit all the assignments before the deadline.
Hello.
Yes.
Hello, Rucha ma'am.
Yeah.
You explained regarding the two data sets, that is BSQ and BIP. Are they same?
BSQ and BIP.
Hmm.
No, they're different.
How they are different?
So, in the BSQ format,
Hmm.
all the pixels in each band, they are so each band will be saved as a band first. I mean, each band will be saved as a separate files. And the second one you said BIL, right?
BIL.
Yeah. So in BIL, all the three bands. So the first, each line of every band is read. So it's first line of first band, then first line of second band, then first line of third band, and so on.
So I cannot find any difference between BIL and BSQ.
Uh,
Am I correct?
See, I think you might be a little confused because of how we wrote it.
Okay.
So, yeah, so this BSQ, don't get confused because of the representation. So, when you are reading an image, it will read the whole band one first, band two first, band three first. I
Line
mean,
by
it will
line.
read an entire band one, band two, band three when it's reading a BSQ file. But when
Right.
it's reading a BIL file, it will read first line of band one, first line of band two, first line of band three, and so on.
That I wanted to say that is there any change in BSQ or and BIL or not?
So,
Do you find any change?
hello.
Hello, madam.
Huh. Did you get it?
No. BIL I cannot get it. So can you explain it on a separate page or as
Okay.
per your
So
convenience?
when you're reading when you're reading a BSQ file,
No, BSQ is fine, sir, madam.
huh.
BSQ is fine. Let me know how to write the format that is BIL.
Okay. So in BIL, you when you're reading the file, this first line will be read,
Okay.
then this first line will be read, then this line will be read, then second line of the first band, second line of the second band, second line of the third band, and so on. But when you are reading a BSQ file, in that case, this will be read first. All this first line, second line, third line. Then here first line, second line, third line, and then first line, second line, third line.
No, no, I wanted to know the way you are represented in BSQ and BIL. Are they same or?
Yeah, see, this is just a way of representation, but when the file is being read in the system, it will be read differently.
Okay.
Huh.
Overall presentation is similar.
See, BIL, you can write it like this also. First line, second line, third line. Then first line, second. I mean, band 1, band 2, band 3, band 1, band 2, band 3, and so on. We'll discuss this in the next lecture. I'll try to explain it better.
Okay, okay, thank you.
Okay, okay.